We will now begin our study of group theory. The concept of a group got its origin back in the 1800s, and specifically in the 1820s when mathematicians were investigating solutions to quintic polynomial equations. Our current formal definition of a group goes back to the year 1882 with the work of Walter van Dyck. Before we give this formal definition of a group, we need to first define a binary operation. A binary operation on a set G is a function defined from G cross G to G. Usually binary operations are defined multiplicatively. So let's just say multiplication is a function from the product of G with itself to the set G, where you take an ordered pair in G cross G and it gets mapped to the element AB. We're very familiar with many binary operations. Our standard operations of multiplication, addition, and subtraction are binary operations on the real numbers. Okay, so multiplication, addition, subtraction are binary operations on the real numbers. Division is not a binary operation on the real numbers. Because we can't divide by 0. Now that we have defined a binary operation, we can give our formal definition of a group. A set G that's closed under a binary operation. So let's say the binary operation is multiplication. So again, we're going to write this multiplicatively. The element AB gets sent to the product A times B. Given a set G that's closed under a binary operation, multiplication, together this pair is called a group if the following three properties hold for this pair. First, we have the associative property. That is, for any elements A, B, and C of the set G, the product of AB with C equals the product of A and the product BC. So we have the associativity of our elements. Secondly, we have an element called the identity. So there is an element which we'll call E, which stands for the identity. There's this element E such that for any element A in G, A times E equals E times A, and that just equals A. And the third condition is every element in the set has an inverse. So for every element A in the set G, there exists another element called the inverse of A, such that A times the inverse of A equals the inverse of A times A, and that will give the identity element of the set G. So a set G that's closed under a binary operation is called a group if the set is associative, there's an identity element, and each element has an inverse. Some more definitions. The group G with its binary operation multiplication is called abelian or simply commutative if A times B equals B times A for every elements A and B and G. So when dealing with common sets of numbers like the real numbers, we kind of take this property for granted, that the order of a product doesn't matter with real numbers. So the real numbers under multiplication or the real numbers under addition would represent an abelian group. A group G under multiplication is called a finite group if G is a finite set. Now let's give some quick examples of common groups. The set of integers under addition is a group. To verify this, we need to show that the integers are closed under addition. It is true that for any integers A and B, A plus B is an integer. So the integers are closed under addition. And we need to verify the three conditions of a group. First, associativity is true. We know that A plus B plus C will equal A plus the quantity B plus C for any integers A, B, and C. We know that the real numbers are associative. We have associative property for all real numbers, and so the integers being a subset of the real numbers, we have associativity. Secondly, we do have an identity element. The additive identity for the integers is the integer 0. So A plus 0 equals 0 plus A equals A for every integer A. Thirdly, every integer A has an additive inverse called negative A. So A plus negative A equals negative A plus A, and that equals the additive identity 0. So the inverse of A is negative A for all integers a. Therefore, the integers under addition forms a group. Further, because addition is commutative, we see that this is actually an abelian group. So since a plus b is the same as b plus a for all integers a and b, we see that this is an abelian group. Similarly, we see that the rational numbers, the real numbers, the complex numbers are all groups under addition. And the identity is 0, and the inverse of any element a will be the negative of a for every element a. If we take out the number 0 from these sets, we can actually define a group under multiplication. So the rationals, the non-zero rationals, the non-zero real numbers, and the non-zero complex numbers are all groups under multiplication, but so are the positive rational numbers and the positive real numbers. So these are all groups under multiplication with multiplicative identity equal to 1, and for any element a, the inverse of a is 1 over a. Since we're excluding the number 0 from these sets, we can define the multiplicative inverse as 1 over a. Another example of a group is the set of integers mod n. This set is an abelian group under addition of residue classes. The set of equivalence classes which have multiplicative inverses mod n is also an abelian group, but it's an abelian group under multiplication. So it's an abelian group under multiplication of residue classes. By definition, this set contains all the equivalence classes with multiplicative inverses, so this set forms a group under multiplication. Now let's present an introductory theorem about groups. Let G be a group under the operation multiplication then the following four statements are true. The identity of G is unique. In other words, there's exactly one element in G that is the identity. Secondly, for any element A in G, the inverse of A is unique. So there exists a unique inverse element A inverse in G. Thirdly, for any element A in set G, the inverse of A inverse equals the element A. And fourthly, if I have a product AB, then the inverse of the product AB equals the product of the inverse of B with the inverse of A. So let's prove these statements. First, the proof of statement 1. Let's suppose we have two identities in the set G. So suppose E and E prime are both identities of G. Then E equals E times E prime, by definition of E prime being the identity. But since E is also identity, if I multiply E times E prime, that's the same as E prime. Thus, the identities are equal. And we see that there must be only one identity element in the set G. Now, the proof of statement 2. Suppose that A has two inverses. Let's let B and C both be inverses of element A. And let's let E stand for the identity element of G. Then by definition of an inverse, we see that A times B will have to equal the identity E. But for similar reasons, if I multiply C times A, I will also get the identity element E. Then, combining these statements, we see that if I start with the element C, that's the same as C times the identity. And we've already written the identity as A times B, so this equals C times the product AB. By the associativity property of the group G, I can write this as the product of C and A times B, but C times A is the identity element E, so we have E times B, but by the property of the identity, E times B just equals B. Thus, from this chain of equations, we see that C and B must be equal. Therefore, A has a unique inverse element in the set G. Now for the proof of 3. Consider this expression, the inverse of A inverse. By definition of an inverse, this is the unique element Now we know that inverses are unique. So this is the unique element of G such that A inverse times A inverse inverse equals A inverse inverse times A inverse, and this equals the identity element E. But if we replace A inverse inverse with the element A, we see that the inverse of A inverse must be A. Since A inverse times A equals A times A inverse equals E, and we know that inverses are unique, we see that A inverse inverse must be A. So in other words, A is the inverse of A inverse. For the proof of the fourth statement, let's assume that A and B are elements of G, and look at the product AB times B inverse A inverse. Since G is associative, I can rewrite this product as A times the quantity B times B inverse times A inverse. By definition, B times B inverse equals the identity. So this is A times E times A inverse. Multiplying A times the identity E just results in A, so this equals A times A inverse. And again, by definition, this equals the identity element E. Similarly, B inverse times A inverse times the product AB will equal B inverse times A inverse times A times B. The product in the middle will reduce to the identity element. B inverse times identity will just be B inverse, and then B inverse times B equals the identity. Therefore, we see that the inverse of the product AB must be equal to B inverse times A inverse. And this finishes the proof of this theorem. Now it's important to note that nowhere in the proof of this statement do we assume that the group G was abelian. So we can't change the order of any of the factors in the products when we're proving these statements. Now for some quick notes about the notation of groups. So technically, a group is a pair. It's a set G with a binary operation. But we know what the implied operation is. We often just drop the operation and just say that G is a group. So we often write a group as G, and just assume that the operation is multiplication. When it's assumed that the operation is multiplication, the identity element is often denoted by 1. And if we have a product of an element with itself many times, we want to use our normal definition of an integer exponent. So for an element in the group G, the product x times x times x times x, a total of n times, is denoted by x to the power n. And if we're multiplying the inverse of x times itself, a total of n times, this is similarly denoted as x to the minus n. So we also use the convention that x to the power 0 would represent the identity of G. This next theorem establishes the cancellation property of groups. If A, B, and C are elements in a group G, and either of the following statements is true: if AB equals AC, or B times A equals C times A, then we can conclude that B equals C. So if we have multiplication by A on the left or multiplication by A on the right, we can simply cancel the factor A and conclude that B equals C. So we have a left cancellation and a right cancellation rule for elements of G. For proof, let's look at the expression AB equals AC. So if AB equals AC, then we can multiply both sides of this equation on the left by A inverse. We obtain A inverse times the quantity AB equals A inverse times the quantity AC. Then by the associativity of group G, we have A inverse A times B equals the quantity A inverse A times C, which implies the identity times B equals the identity times C, and by definition of the identity, we can conclude that B equals C. So this establishes the left cancellation rule. The proof of the right cancellation is similar. So this establishes the left and right cancellation rules for groups. Next, we will define the order of an element in a group. For a group G, and an element A in G, we define the order of A denoted by A with absolute value bars, the order of A is the smallest positive integer n such that A to the power n, so A times itself n times, equals the identity element E. It could happen that A to any integer power never equals the identity element. So if, in this case, if no such n exists, we say that the order of A is infinity. Let's look at a quick example. Consider the group of non-zero real numbers under multiplication. Okay, so the identity element is 1, and we see that the order of the identity element is always going to be 1. The order of the real number -1 is 2, because -1 squared is equal to 1. But every other element of the non-zero reals has infinite order. Because if you take any other non-zero real number and multiply it times itself, it will never equal 1. Now let's discuss Cayley tables for a group. Cayley tables were named after Arthur Cayley, who first introduced these tables in 1854. So given a finite group, a Cayley table is a matrix that shows all the possible products of elements in the finite group. Some authors call these tables multiplication tables or simply group tables. Let's give a simple example of a Cayley table. Let G be the group with two elements, 1 and -1, under multiplication. So then the Cayley table for this group, you would write the elements in a row on top and in a column to the left. And so we give all the possible products. Well, 1 times 1 would be 1. 1 times -1 would be -1. -1 times 1 is -1, and -1 times -1 is 1. So this is the Cayley table for this group. So again, it lists all the possible products of elements in this group. Let's look at a little more interesting example. Let's let G be a group containing 4 elements, the identity element 1 and elements A, B, and C. And suppose this group has the following Cayley table. Clearly the first row, 1 times 1 is 1, 1 times A is A, 1 times B is C, and 1 times C is C. In the first column, A times 1 is A, B times 1 is B, and C times 1 is C. The second row will define A times A to be 1, A times B to equal C, and A times C will equal B. And so then filling this out, B times A will be C, B times B is 1, B times C is A, C times A is B, C times B is A, and C times C is 1. So this establishes all of the possible products for elements in the group G. So the standard convention is that the row factor comes first and the column factor comes second in a product. So from this Cayley table, we can tell a lot about this group. We can see if a group is abelian. And notice that when you draw the Cayley table, every element shows up exactly once in each row, and every element shows up exactly once in each column. So each element shows up exactly once in each row and column. Now notice that in the second row, we see that A times B equals C. And in the third row, we see that B times A also equals C. Similarly, if I look in the second row, A times C is B, and in the last row, C times A also equals B. From the third row, we see that B times C is A, and in the fourth row, C times B is A. So therefore, we can establish the fact that this is actually an abelian group. Further, look at the diagonal of this matrix. We see that the identity appears along the diagonal. So in other words, A times A is the identity, B times B is 1, C times C is 1. So we see that each element is its own inverse. This is actually a very famous group with 4 elements. It was named by Felix Klein as the 4 group, so we call this the Klein 4 group. So this is the famous finite group called the Klein 4 group. And in German, that's pronounced Vier group. So this group is often denoted as V4. For the Vier group, or some texts use K4 for this group.